Maybe, but it's comes naturally, it's not forced. So in this case where if you had a large mineral deposit, right, the government incentivizes that everyone just builds mineral deposits and a bunch of money. But in the finance sector, although yes, there are regulations with the finance sector in the UK, it came about more naturally. It came about from competition.
Yeah, it doesn't really matter though, does it? Because I think the essence of it is that, you know,
I think
it's not really. Yeah, but like if you're not in finance, you're struggling, and even if you're in finance, you're still struggling.
Yeah, it sucks.
Like I feel like
If you're in the UK, you're struggling.
yeah.
But I think that's a UK problem, not necessarily a finance problem.
But how can you separate the two?
I think probably the UK has to do with the finance industry. I think it's to do with ACEs or regulatory decisions over the course of the last 50 years. Margaret Thatcher, for example, refusing to build public homes, cut housing supply. In fact, London, per 1,000 residents, or I think either 100,000, has built 8 homes in the
But
last
can you
year.
really separate?
That is lower than New York.
But can you really separate house prices and finance?
I think you can. I think house prices are determined predominantly by the restriction of the supply of housing in high demand areas. Yeah, people want to work in London because of the high value jobs there, I think.
That wrong? Just a minute. Okay, so the code for today is 233659. Right.
Maybe, yeah.
Okay, questions on what we did on Tuesday. So we started our first model of money, and finite horizon economy. I'd written down the first order conditions first, and then I tried to motivate, yeah.
Sorry, the code isn't working.
No?
I would have to check because I wasn't sure if
Well, I can always sign you in if I remember to. That's within 657. My apologies.
Cheers. Thank
That's
you.
good, yeah.
Okay. Thanks. So there was the Euler condition, which is in some sense the key thing that is different from what you've done with Lagrangians, etc. before. You might have seen that in macro, but I'm not quite certain. So the idea is there is an intertemporal component. You need to decide on giving up something today in order to get something tomorrow. And in general, that's not such a problem. It works exactly in the same way as a relative price, except that if you're dealing with either a commodity which has a non-negativity constraint that binds, or in the case of money, a non-negativity constraint that might bind, there the condition has to be written differently because it could be an inequality. Okay, that's basically the point that we made on Tuesday. The key point being that you might actually be better off moving to holding a negative quantity of money, but you're not allowed to. And therefore, at the margin, the computation that you look at incorporates that fact, and that's where you get an inequality. Okay, so that's what we've done. What I want, and then I had written down the Lagrangian for that particular problem. And I'm going to start now with the Lagrangian and then derive the first order. So, what we had written, and hopefully these pens will work reasonably well, so we will be able to write everything that I need today without spending too much time. 0. Okay. So my Lagrangian for agent I depends on the choice variables. So consumption of the single good at date 0, the amount of money that the agent decides to carry at date 0, so on at every date. Oh, there are other things that I need to incorporate. Those are not the only variables. Of course, prices and things, which I'm also going to not use here, but the multipliers of our so-called endogenous variable, if you'd like to. Lambda 0, sorry, lambda I 0, lambda I t, and then you have rho I 0, rho I t, and mu I 0, mu I t. So it's a function of all of those variables, and the function was, well, we have the sum, time going from 0 to capital T, beta t, ui, xit, that's the payoff, the utility, and then you have all the constraints. I haven't rewritten the optimization problem. We've written that the last time. You have it on your notes. There's too many things to write on the board, so that's why I'm not going to do that. So you take the multiplier, and then you take the constraint written in a particular form so that your inequality points towards the right, so to speak. So that form is et omega it plus qmt mi t minus 1. So these are your resources at date t minus et xit minus qmt mit. So this is what you wish to purchase of the good and of money. Yeah, there's nothing here which is specific to the one good case. It's just that the one good case makes the point, which is why we're doing it. In addition, you have two other sets of constraints. One is non-negativity of your consumption, so rho it, xit, and non-negativity of money holdings, so that's mu it, mit, and you're given the initial value for m, which we won't incorporate in the Lagrangian. Is that okay? Questions, please ask. If there's something that's not clear to you, Tom, you should ask. Okay? Yeah. So now, the first order conditions, we'll obtain these by taking the derivative, and they're called the Kuhn-Tucker conditions, because there will be something more than just the derivatives. And I'll tell you exactly what we have. There'll be a whole bunch of things. Okay? So let's take the derivatives first. So you have, with respect to xit, right, xit appears there, so as usual, you get beta raised to the t, u prime, ui, xit. Xit also appears there, so you get lambda it, and then minus pt. You can write that directly as minus pt if you wish to. And it appears there, so plus rho it equals 0. Is that okay? Yeah. Just make sure that you follow what we are doing. Next, we're also choosing mit. Now, mit, of course, appears at date t, and therefore, I'm going to pick up lambda it times minus QMT. Okay? And then it will also appear at date t plus 1, which is when I use the money. And therefore, I'm going to pick up plus lambda I t plus 1 QM t plus 1. This is the bit that is often a problem, because you just look at that and you see MIT just there and you say, that's it. Well, no. We are not writing down the Lagrangian in great detail, but we have all the information there. You have to bear in mind that the money that you buy today will get used tomorrow. And therefore, when you calculate its marginal benefit and cost, you need to incorporate that. Is that okay? And then, of course, it will appear there. So you get plus mu IT, and you set it equal to 0. Okay, so this is for all t. Going from 0 to capital T. This one for t going from 0 to t minus 1. And you see why? Because you also have what happens at the terminal date. Well, at the terminal date, you will have MIT over there. So you will get lambda I capital T minus QM capital T. But there is no next period in which you get to use the money. Okay? So you will get that term, and you will of course get the term that you pick up from here, which is mu I capital T equals 0. And that, of course, is at capital T. So I don't need to write anything more on this. Is that okay? Questions? Anything that's not clear? There will be more. That's not the only thing. There will be a lot more. Yeah?
You should go over the t plus 1 thing again.
Yes? So you need to, so you're taking the derivative. So you need to see where does the variable appear. It does not appear there. Money does not give any direct value to you in terms of utility by consumption. So it appears in that constraint, but it appears at two different points in time. It appears at date t and also at date t plus 1.
So it's t minus 1 though, there, no?
This is at date t.
Mm-hmm.
Over here it says MIT minus 1.
Yeah.
That's not the variable I'm looking at now.
No.
But MIT will appear in that position at the following date.
Ah, okay. Right.
Right? Fairly clear. There's nothing very surprising. But you have to keep that in mind when you take the derivative. You have to think in terms of what is it that I'm looking for? Well, money that I buy today is getting used tomorrow. And therefore, I have to incorporate the effects of both. One will be negative, one will be positive. Is it okay?
Yes.
Something that's not clear? Go on.
With the lambda I,
Yeah.
capital T,
Yes.
QM capital T, is the mu I supposed to be t minus 1 if it's for all t to t minus 1?
No, it is t. The reason is I'm taking the derivative over here with respect to mi at capital T. Where does mi at capital T appear? It appears there.
I see.
Yes? Okay? And it's going to appear there. Those are the only two places in which it appears. So I get two terms. The reason is there is no tomorrow. There is no capital T plus 1 for this economy. The economy ends at capital T. And that will be crucial to the argument. Remember, all this is about the argument as to whether money can have value, which I haven't gone into so far, which I will. We are developing the material that will allow us to make that argument. There will also be a cheap argument, okay, which you should know, which is the easy one, but that's not the one that you should be giving if you're asked to check this. Okay? So, these are called the first order conditions. And as I said, that's not all that you're going to have. You also have a set of conditions which are called complementary slackness, which are exactly what we have here in terms of the constraints. But, sorry, in the form in which we have things written in the Lagrangian. But I will write it out. Okay, so at each date, you want that term to be 0. Okay? I don't know whether you saw this when you were taught Kuhn-Tucker. You probably were. You must have. If your Yogesh taught you all this, you would have done it carefully. In addition, you will have the same condition for your other constraints. So rho t, xit equals 0, again for all t, and mu it, mit equals 0 for all t. As I said, this is called, or these are called complementary slackness conditions. The idea being, what it's saying is the following, that quite literally, your constraint times the multiplier is 0. Okay? In a moment, you will see that it's actually saying much more than that because of some other condition that we have. So that's complementary slackness. All the multipliers will be non-negative. When you do constraint maximization with an equality constraint, non-negativity of the multiplier needs to be proved separately. If you remember, I showed you the interpretation of the multiplier. Okay, here the multiplier has the same interpretation, but in the Kuhn-Tucker theorem, this is something that you, depending upon whether you're looking at necessity or sufficiency, over here we're looking at necessity, necessarily, so if you're at a solution, there will necessarily exist non-negative multipliers. That's because of the way we wrote our constraints. That's why it's important to write the constraints in the form in which I've shown you. If you don't, things will get messed up. Is it okay? Make sure that you write the constraints in the way you will find them in the notes, which is all of this greater than or equal to 0. That one greater than or equal to 0. That one greater than or equal to 0. That's where the multipliers come in. Okay? So these are non-negative multipliers. And in addition, you also have all constraints must hold as inequalities. That's always the case. After all, that's part of your problem. As inequalities, which is not necessarily as equalities. They can hold as equalities. That's possible. But they're required to hold at least as inequalities. Yes?
I was just
Yeah, sure.
how did you go from the first order conditions to the
You don't. I didn't say you get from one to the other. These are separate conditions. So you have, when you have inequality constraints, you have additional conditions. With equality constraints, you had the constraints must hold and the first order conditions. And there exists a multiplier for each constraint. Since we have an inequality constraint maximization problem, over and above the first order conditions, you must also satisfy complementary slackness. And I'll say a little more about it in a moment as to why it's important. You must satisfy complementary slackness and you must satisfy non-negativity of multipliers. These are additional properties that you did not have in the standard Lagrangian.
Yeah. This is just like from theory.
There's the maths behind it, yes.
Yeah, okay.
There is the maths behind it, which we are not developing.
Yeah.
But the condition that we will get by doing this will be exactly the same condition as I derived on Tuesday intuitively.
Okay.
Is that okay? Okay so far? All well? Yeah? So what are we going to do? Well, we of course, these first order conditions look a bit different compared to what we had. So let's see how we go from one to the other. So now, if a constraint holds as a strict inequality, we are looking at a solution. Suppose that the solution, the constraint holds as a strict inequality. That can happen. For whatever reason, the constraint is really not constraining you, in the sense that you can move around a little bit within that constraint and you will still be within the feasible set. But you don't want to. Why? Because you're already at a maximizer. That can happen. Okay? So if a constraint holds as a strict inequality, what's going to happen? Suppose that constraint, or suppose that one, which is more relevant for us in some ways. Suppose at the solution, Remember, these are necessary conditions. So we're saying, suppose you're at a solution, what's true? Suppose at your solution, the amount of money you're carrying is strictly positive. It can happen. It typically will happen, right? But then complementary slackness says your multiplier is 0. Is it okay? Is that clear? So what is it telling you? It's telling you if the constraint does not bind, it's as if around the point that you're at, you can ignore the constraint. So if I were to slacken your constraint, it's not going to make any difference to your solution. The value of an additional unit of slackening that constraint there, which means moving the 0 to the left of 0, to negative values, makes no difference to you. Even increasing it by a little bit from 0 will not make any difference to you, so long as you increase it by very little. Is that okay?
What do you mean very little? Like,
So suppose your solution is you're carrying 3 units of money.
yeah.
Okay? My constraint could become from 0, the right hand side of the constraint, could become -1, it could become +1, it doesn't matter.
Okay, no, not much then.
Sorry?
That's
Yes, not much, that's the whole point. You see, this is one of the things that you really don't pick up when you do calculus. Calculus is about small changes.
Yeah.
How small, you're never clear about. It's just sufficiently small. So there is some change, it's not 0, it's some sufficiently small change, and you're still all right. That's all that it's telling you. That's always what calculus is doing, in terms of derivatives. Okay? This is why in economics we often impose concavity or quasi-concavity, to say that what is happening locally is also giving you the entire picture. For that you need second order properties. The first order property simply says that something, so there is some sufficiently small change which will not make any difference to what you're doing. Is it okay? Is it clear? Yeah? So, if a constraint holds as a strict inequality, then from complementary slackness, which I'm going to write as CS, the corresponding multiplier must be 0. This is important. Because it allows me to write my first order conditions in a different way. Okay, which is the way you've seen it. So let's take that first order condition. Right, now I know, now please pay attention. The way I have it written here, I have this additional term, which is either 0 or positive. Right, it's either 0 or positive. And therefore, if I get rid of the term, I can replace my condition with an inequality. Okay, so that first order condition becomes beta t u prime I xi t minus lambda I t pt less than or equal to 0. I simply drop the rho I t. I can if I wish to. Is it okay? It's either 0 or positive. So if I drop it, I get that sign. Right? When is it 0? Okay? When will I get an equality? Well, suppose rho is actually 0. When will rho be 0? When xit is strictly positive. Is that okay? So when xit is strictly positive from complementary slackness, rho has to be 0. And therefore, I can write this as with equality if xit strictly positive. Which is what you have seen with Jorgen. Make sense? It probably made sense when you saw it with him as well. Okay? But this is a different framework. Did you do maths with Jorgen? Did you do maths with our economics students? Have you seen this stuff in economics?
Yeah, first year, yeah.
First year, okay. So it was earlier it used to be taught in the second year, so I remember this is what I was asking. Is it okay? All well? So now, what about the next one? Well, minus lambda it mu, sorry, what do we have? QMT plus lambda I t plus 1 qm t plus 1. Well, once again, less than or equal to 0 with equality if, what's the variable? M. So that constraint does not bind. Okay, this is what we saw on Tuesday. together with the last condition, which again will take the same form, minus lambda I capital T, Qm capital T, less than or equal to 0, equality if Mi capital T is positive. Is that okay? Now, you have to make sure that you've understood what we've done so far, so that on that problem, you are able to write it down correctly. Okay? I would even say, even if you're not given the optimization problem, in general, I will provide the optimization problem to you. But for this sort of a problem, even since this is sort of so key to monetary economics for this class, you should be able to write down the optimization problem on your own, and then write down the Lagrangian, and then write down the Kuhn-Tucker conditions, then write down the Kuhn-Tucker conditions, including each of the four sets correctly, so that you're able to get the argument and obtain these conditions on your own. Anything that's not clear, you need to ask me now. Because now we're starting to move into the real stuff. That's not to say you can't ask questions later, but this is a good point at which to ask questions if you have any. Anything that's not clear, it should be completely clear, hopefully. Is it okay? So now let's go back to what we were actually interested in, which is, can money have positive value in this economy? If it's rationally valued, right? So now, money, by its very nature, we're talking about fiat money, so we better have a positive amount of it in the economy. Okay? There is a positive amount, so I'm not going to write much on the board now, because I don't need to. We've done all the hard work. That's where the hard work is. Getting the first order condition, do it correctly. Keeping in mind that you have a non-negativity constraint. Okay, so now, there is a positive amount of money in the economy, so if we are at a monetary equilibrium, that money must be held by people within the economy. So at the final date, at date capital T, somebody must be holding a positive amount of money. If we are at equilibrium, right? That's our question. Can there be a monetary equilibrium? Suppose there is. So at date T, somebody is holding a positive amount of money, so that first order condition will hold with equality for that person. We agree? Correct? So either lambda I capital T or Qm capital T is 0. One of the two must be 0 for that person. Is that okay? If lambda I capital T is 0 for that person, this over here, even with an inequality, this bit has to be less than or equal to 0. Yes? We agree? Yes?
Why?
Yeah. Why? Very good. So we are saying from here, either lambda or Q is 0.
Yeah.
Suppose lambda is 0 for that agent at date T. This term is 0. Right? So what is left? This bit has to be less than or equal to 0. Both of these are non-negative. It cannot be negative. Can it be 0? Well, at a finite t, beta to the t cannot be 0. When will marginal utility be 0? Marginal utility is 0 if you're satiated. Remember, utility is increasing here. So it could be that this economy has infinite resources and somebody gets everything and therefore they don't want any more because it's just too much. But no economy has infinite resources in our world. Okay? Each step is important. Therefore, that first order condition will get violated. And therefore, QMT must be 0. The price of money has to be 0 at the last state if you are at a monetary equilibrium. The intuitive, hand-waving argument is, look, there is no tomorrow, so why carry money? That is the intuitive, hand-waving argument, which is correct, except that's not the argument you're required to give here. You see why? We're doing the same thing. That hand-waving argument says that if there is a final date, what would you do by demanding money at that date? You can't use it at the next date because there is no further trade. Okay, but this is the formal way of confirming that argument. So now we've shown that Qm capital T is 0. We agree? Go to the previous date. Again, there will be some agent who's carrying money. For that agent, you will have an equality. Yes? We've already shown that at that earlier date, sorry, this is not a capital T. So at that earlier date, which is capital T minus 1, this term which refers to what happens at capital T, will be 0, because the price is 0. That we've already determined. Okay, so this term plays the role of what we saw earlier. Once again, this bit will be less than or equal to 0, and you repeat the argument, which I'm not doing here. This is a backward induction argument that you might have seen in game theory. It's basically doing the same thing. We're saying that if money is to be rationally valued, the price must always be 0. That's the only solution. Yes? No? Maybe? You're missing something? Please ask.
How did you do the for all time periods again?
Sorry?
How did you do the for all time periods?
Yes, you can sit and do it for every time period. This is like a proof by induction.
Yeah.
You can either do 1, 2, and then say n and n plus 1, or you can sit and do 1, 2, 3, 4, but you'll be there forever. Except that over here it ends at a finite point.
Yeah.
Okay? So, but the argument is the following. First, make sure that you understand the argument at date capital T. So at date capital T, the price has to be 0 is what we've shown. The equilibrium price must be 0. Go to the previous period at capital T minus 1. At that date, again, if market's cleared, there has to be somebody who's holding a positive amount of money. Look at that person's first order condition for holding money. Right? This is at date capital T minus 1. That term is 0 by what we've already shown. You agree? So that term must be less than or equal to 0, exactly as we were doing before. And therefore you repeat exactly the same argument. And you're done. Then you can say that this happens at each date. Going back to date 0, the price is always 0. Is that okay? This is how you do a proof. This is the second proof we've seen so far. The first was of the first welfare theorem. This is the second one. You'll see more in problems inside in class. Anything that's not clear? Now, of course, if you could artificially generate demand for money at the last date, for example, by insisting that you have to pay taxes, which you don't have here, and your taxes must be paid in money, okay, fine. You can fix it. You can fix it in some other ways. But this is an economy in which we don't have those features. So in a finite horizon economy, money cannot have value. Are we okay? Can we proceed? Questions, please ask. Anything that's not clear?
When you introduce loans and assets, can money have value?
Sorry?
When you introduce loans and when you just introduce loans, can money have value? Or you can have negative money.
Why are we not introducing loans?
I mean, can money have value when you introduce loans?
In this economy?
Not in this economy.
No, I understand. What you're saying in a finite horizon economy.
In finite horizon.
No. It will not make any difference. The same argument will work. The reason is, you could have a market for loans, but you do have a positive amount of money, that's fiat money, that's available. Okay, so the market for loans will give you additional first order conditions, etc. But these conditions will continue to be the ones that you get for money.
So long as you have a positive amount of money in the economy.
If there's a positive amount of money and there's a terminal date and it's rationally valued, its value must be 0. Yes.
If you have a negative amount of money?
You can't. Okay?
Yeah.
The stock of money that we think of is always a positive one. That's what. So this is this old sort of literature, or I don't know whether these things get taught anymore, but there used to be a distinction between inside money and outside money. Inside money is essentially loan markets.
Yeah.
Okay? So you net that out, what you're left with is outside money, and that's 50%. Okay, you relate that to wealth in the economy, so some people used to do that. You get into stuff that we really can't talk about here. You need to have a proper model to talk about these things. It's just easy to saying things is cheap. You say whatever you want to. Yeah, and it's correct. And very often it's correct, but very often it's not correct. You don't know. This sort of stuff, there's a concrete answer. You say, I don't like the model, that's fine. Is it okay? Something's bothering you.
Yeah.
Yeah, go on.
It's just
You need to ask.
the bit where you get to all constraints must hold.
Wait.
Holders inequalities. Yeah, I just don't understand how that's
Which one?
bottom of the left side.
This one?
Yeah.
This is simply saying that part of your necessary conditions is the statement that all your Lagrange multipliers are non-negative.
Is that why is that something you're bringing into the model, or is that something?
That comes from the maths.
Okay.
If you set up your optimization problem in that form, and if you are at a maximizer, at a solution to the problem, then there is a result which says that the following conditions must hold. These are the conditions.
Was there
So non-negative.
Non-negative multipliers, that's right. As I said, that has to do with the way the constraints have been written. That's important. If you don't write the constraints in that form, you write them in the way we typically write constraints, you can still state a result, but that result will have different statements in it, and you'll end up very confused. So just my request is in this class, please stick to that particular way of writing the optimization problem. And this is for a maximization. For a minimization, you need to do things carefully, separately. We're not getting into that.
Right, can I take a photo of the board?
No, you don't need to. You have everything in your notes. You have everything in your notes. And remember, if there is something that you haven't understood, ask me. Come to my office, ask me in class, just do it. I want you to get away from the idea that you need the board. Make your own notes if you wish to. That's fine. Okay? Make your notes, because that's why the notes have been given to you, so that you're familiar with what is where, and you can make any annotations that you wish to. I just strongly recommend that that's a better way for you to work. And the notes are also on the VLE page, so if you wish to make notes on your laptop, you can do that. It's just that the printout is easier for some people, which is why earlier I used to give just printouts and nothing on the VLE, put everything on the VLE, but I realized that students are better off very often with the printout in class. So that's why you have both. Questions? Anything that's not clear? So what we want to do next is the following. So this is, suppose money is naturally valued. What we are getting to will be models. Now you see why things will become more complicated, because we have to look at economies that go on forever. We have no way out. We have to. And therefore you can't really give all these intuitive arguments anymore. There'll be some intuition, but a lot of it can't be given. Okay, but before we get to that, there is an intermediate model which I want to cover. Yes?
Sorry.
Answer the question.
Okay. I was just wondering if there was like an interpretation for the Lagrange multipliers in.
It's exactly the same. The Lagrange multiplier always has the same interpretation. It tells you, this is why, if the constraint holds as a strict inequality, this is what I explained earlier. If the constraint holds as a strict inequality, then in terms of small changes, it's as if you don't face that constraint. And that's why the multiplier is 0. That's exactly what constraint qualification is doing, complementary slackness is doing for you. So the interpretation is, there the size is 0.
If it's not 0.
If it's not 0, the interpretation is exactly the same. Suppose you slacken the constraint. What does it mean to slacken the constraint? This you need to think about slightly differently. So in terms of the budget constraints, it simply means either you increase or decrease the value of your endowment and the money that you carry. Okay? So if you were to increase that by 1 unit at date t, the increase in your maximized utility will be exactly lambda IT. It's the same interpretation. This is why we did the interpretation, but it sounds like a long time back, but it was last week. That's exactly why we did that interpretation. Because from here on, a lot of the stuff will be done just in terms of multipliers. It look like this is just maths and maths and maths. And yes, but that's about the only way to do things so that you can get somewhere. And it's my job to try and explain it to you. And do it correctly. Yeah.
With the zero value in a finite time horizon.
Yes.
Can also be understood by saying if you had a limited amount of time to spend all of your money on actual resources, you would spend all of it because the money, you can't use it anymore after that period.
The important thing is that you can't use it after that period.
Yeah. So in that finite time horizon, you want to spend all of it so you get something.
You could call it that. If you wish to, you could think of it in those terms. Okay. But as you see, as soon as you start using words to do that, right, you're not really giving much by way of the argument. Why is that happening is what we are digging out here. But yeah, as I said, the intuitive way to think about it is, why would you carry an asset into a period in which you know that asset cannot have any value? You won't. Therefore, the price, you would, provided the price of the asset is 0, nothing else. And that argument is formalized. Because from then you need to figure out why it must be 0 always. Is it okay? Yeah. So what we want to do now, let me see how far I can get, but is I want to talk about a situation in which the horizon is finite and yet money would have value because people's expectations need not be correct and in this case, we are not looking to solve for an equilibrium in all markets at the same time. So this is a much more realistic description of the economy, and it goes back to, you've heard the name Hicks? John Hicks? You have, right? So this is one of the greatest economists that the world has seen, British. He won the Nobel Prize with Arrow in 1972. Hicks is famous. Hicks started initially he was either doing maths or classics, I don't remember now. But after that, he went to economics. He did a lot of work on labor economics. But then he got interested in general equilibrium. And Hicks has a book from the 30s, about the same time as Keynes. Okay, and this is important because when Keynes wrote his general theory, okay, you probably know, Keynes, his initial training was as a mathematician. Keynes also has some important work in probability. Okay. When he wrote his general theory, basically nobody understood what he was talking about. That thick a book, nobody understood what he was saying. I think it's fair to say nobody. Hicks was the person who wrote a 10-page paper in econometric at that time, which was a very recent journal. It's one of the best journals in the profession. It had just started, and Hicks wrote a paper where he explained what Keynes was doing. This is the ISLM. Hicks was the person who got it across to people. Okay, and he did it carefully because Hicks was working on general equilibrium at the time. And Hicks, when it came to general equilibrium, Hicks said, look, a more realistic description of the economy is people have beliefs about what will happen tomorrow, including about prices. So they have beliefs about budget constraints tomorrow. They need to take decisions today. Markets exist for today. So they will look at the prices that are quoted today, they will look at their expectations for prices tomorrow, and based on that, they will come up with their demands. Markets will clear today, and then you move to tomorrow. And Hicks called this entire process a temporary equilibrium. And the reason economists have stopped dealing with temporary equilibrium, although there is some work that continues, is because it gives too much flexibility in how you describe the economy. Okay? Lots of things can happen in a temporary equilibrium over time, and therefore you have less control in terms of predictability, which is why people have gone to rational expectations, which has its own problems. But that's not what I'm getting at. So I'm going to describe the economy. Let me actually write on this side because this is too extreme place to write things. So I'm going to erase on this. You'll also get a bit of economic history and thought in the course of this class. Okay, so there are two dates. Only two, just to keep things simple. 0 and 1. One, physical good and money, fiat money. Okay. Two individuals, A and B. Not that it matters. The price of money is always equal to 1. So QM T equals 1. And we have prices at date 0 and expected prices at date 1. Okay? So the maximization problem is maximized by choosing xi0, mi0, xi1, mi1. Okay, there are two goods there at each date. Sorry, one good in money. I start getting tired at some point. UI xi0 plus beta UI xi1, and your budget constraints, well, at date 0, you have a sequence of markets in the way we've developed it. The difference will appear very quickly. xi0 plus the price of money being 1, mi0 less than or equal to p0 omega I0 plus mi minus 1, which you're given with a multiplier lambda I0, and then PE1 xi1 plus any money that you decide to buy at date 1 less than or equal to PE1 omega I1 plus MI0 multiplier lambda I1, and then you have your non-negativity. Xi0 greater than or equal to 0, Xi1 greater than or equal to 0, Mi0 greater than or equal to 0, Mi1 greater than or equal to 1. I'm not writing out those multipliers, and you're given an initial value of Mi that you carry from the previous data. Okay? Now, I'm going to draw a figure. So I'm going to have xi0 here, and I'm going to have xi1 here, and I'm going to have an endowment that's my endowment point. In a moment you'll see as to why I'm doing all that. And then I'm going to draw a line here where this distance will be mi minus 1 divided by p0. And this I'm going to call my liquidity constraint. So the idea is that if I look at my first constraint and I forget about the fact that I'm going to carry some money, right? Then it gives me the amount of the good that I can purchase using my endowment and the real value of the money that I start with. It's exactly this. That's my endowment at date 0. That's the real value of the money that I started with. So that's my liquidity constraint. Is it okay? Yeah? And I'm going to have a budget constraint, an intertemporal budget constraint, which looks like that. Write it out. So what am I doing here? First, I am going to specify that price expectations, I can do that without putting in price expectations, but let me do it together. Price expectations at date 1 will be formed using some function of prices at date 0. Okay? So my price ratio over here will be given by P0 and psi of P0. The slope of that line will be given by that combination. In other words, since the expectations function is fixed, it only depends on P0. So as prices today change, my expectations will change. Now how do I work out my budget constraint? Well, the simple way to see it is let me add these two. Okay? So if I add them, that will eliminate the mi0 on the two sides, and I will be left with P0 xi0 plus P1e xi1, and in the same way as I dropped out mi0 from the liquidity constraint, I'm going to drop out that one. So I'm left with P0 omega I0 P1e omega I1 plus the money that I started with. Right. Of course, I might decide to have a demand for money at date 1, but in the intertemporal budget constraint, I'm roughly speaking ignoring. Now the point is the following, and we'll stop in a moment. Now what I want to do is suppose it is the case, suppose I tell you that you can work out the value of that point there. So let me write that. Omega I 0, and the second coordinate is going to be omega I 1 plus psi of P 0, sorry, M of I minus 1 divided by psi of P 0. So that's my endowment when young, at date 0, plus my endowment when old. Added to that, I get the value of the money if I were to use it at date 1. Now suppose my indifference curve, just suppose my indifference curve at that point were to slope like that. Okay? Just suppose that that's the case. At those prices, in which direction would you wish to go? Which good would you wish to consume more than your endowment? Good 0 or good 1? That's your indifference curve.
0.
Yes, good 0 for sure, exactly. Is that okay for everybody? If my indifference curve has, the slope has drawn, then I wish to move in that direction. Is that okay? Now, suppose that is true for both agents. Then I will wish to move in that direction. Is that okay? Suppose that is the case for both agents at every P0. Then regardless of what the price the auctioneer calls at date 0, both agents wish to move away from that point. There is no equilibrium. Okay? So what that condition is actually telling you is, somebody's waiting outside. So I'll pick up on this one on Monday. I'm not going to draw the figure again. What I'm going to say is the following, that you can start with a condition at that point, okay, in terms of a marginal rate of substitution. By concavity of the utility function, having a configuration over there will give you the same property at the black dot, and therefore, having the condition over there, which is on the basic economy, let me just write the condition there, the one that we impose. Okay, so suppose